Hey everybody, and welcome back to I Hate Chemical Engineering. This is going to be our fifth video in the THERMO 1 series out of the Smith, Van Ness, and Abbott textbook, Introduction to Chemical Engineering Thermodynamics, 7th and 8th editions. Today we're going to be talking about heat capacity. It'll be the last video before we get to some real examples. Maybe we'll have like a quick recap, of the 5 things we've learned or whatever, the 4 videos before this in the next video, because there is a lot of stuff that you kind of have to learn all at once to really understand thermodynamics, and I hate that it is that way. I was just talking to my this sounds like I got no life. I was talking to my wife about it, saying I just don't know what the best way to go about it is, and the books all try really hard, and I'm trying to lay it out as simple as we can get. So let's just jump right into it, because this could be a longer lesson. So from general physics, you learn the following, right? You learned that the amount of heat it takes to raise a solid liquid gas, by a degree, C or Kelvin, is called the heat capacity. So you learn this equation here, right? You learn that Q equals the heat capacity times the change in temperature. And we define, heat capacity again, and I just said it, but I'm going to say it again, as the amount of energy, so joules here, that it takes to change 1 kilogram's mass, or one, sometimes it's in moles even, but 1 kilogram's mass, 1 degree Celsius. That's in SI units there. And that's basically all you learn in general physics. You don't learn all the nuances behind heat capacity, and especially the nuances in fluids, and that's what we're going to get at today. So first off, let's look at a closed system. So we got a closed system, and let's completely fill it with a fluid. So let's, for example here, let's just completely fill it with liquid water. No air gaps are in the system, and let's put a thermometer in it. So we got a thermometer here. We'll make it pretty, and then let's add some heat to the system. Okay. So again, we said the heat capacity of the fluid is the amount of energy it takes to raise the temperature by a single degree. So in this case, in the fluid, we have a specific example where the fluid is restricted to a constant volume. So we got a rigid vessel, and therefore, volume is constant. So what we call this kind of, this situation is that it's under a constant volume. We have a heat that's going in, and it's going to raise that temperature until it raises it 1 degree. And when it does that, we have what's called the constant volume heat capacity. So we end up with, that equation above, but we end up with, we're going to actually use its differential form. And we're going to use its differential form because, unlike in general physics, the heat capacities aren't always constant with respect to temperature. We'll assume that they are often cases, or at least an average heat capacity will be used. But that's usually a function of temperature is a fluid's heat capacity. So when you look up the heat capacity of, let's say, water, or steam, water vapor, you'll find that the heat capacities are given as functions of temperature. So, what else do we know about the system? Well, if we do a heat balance on the system, and let's do one rigorously just because it's been a while since we've looked at heat balances, we know that the change in internal energy, or total internal energy of the system with respect to time, is going to be equal to the negative delta, or negative change, in the mass flow rate times the enthalpy plus kinetic energy plus the potential energy plus the amount of Q coming into the system plus the amount of work coming into the system or being done on the system. So in this specific scenario, we know that all of that is in fact 0, and what we're left with is that du equals dq. Also, from above, we learned that dq equals cv dt. So in this very particular example, we've actually calculated not only Q, or the change, the differential amount of Q added, or heat added, but the differential amount of heat added is going to be equal to the differential change in internal energy. So to be very specific, because that this is a specific example at a constant volume, when we put this in its most accurate form, we'll end up with this. We have the partial derivative of internal energy with respect to temperature under a constant volume is always going to be equal to the constant volume heat capacity. Right? So what that implies is, that's also going to be equal to the differential amount of heat added with respect to temperature. So, now, is that the only type of heat capacity of a fluid? Well, the answer is no. The fluids have multiple different kinds of heat capacities. And remember, the heat capacity in general is just the definition of what amount of energy or heat does it take to increase the temperature of the fluid by a single degree. So you could define that in a lot of ways, right? I mean, we could say, let's define it under constant volume. But the second way that we're going to define that is under constant pressure. Because it's not often that you have a rigid vessel at a constant volume, right? That's especially full of a liquid, right? If it's full with a liquid, you start heating it up, it's going to blow up, right? You'll add heat, the liquid will try to expand, it'll have nowhere to go, the pressure will become crazy high, at least in practice, right? So let's draw a second situation here. Let's have a vessel that's open top, cup, atmospheric tank, whatever. And let's say that it's got a water level right here. And then let's draw it again. And let's say the water level is now here. Again, let's put our thermometers in here at each point. And we're measuring the temperature as we add heat. And again, let's put our heat coil. So we're adding heat and measuring the temperature the entire time. And as we add heat in the example, we're going to keep adding until the temperature of the fluid changes by a degree. But what we notice is as the fluid, the liquid water heats up, the level changes. And that level change is interesting, right? I mean, what did we just learn about compression and expansion work? Well, when that level changes, that control volume is imparted work on the environment. Right, so now some of that Q that was going to go into changing the temperature now instead went into changing, or doing work on the environment. So that means more energy will be required to raise the temperature of the fluid held under constant pressure, and I forgot to put that. Let's put constant pressure here. In both cases, the pressure on the top of the surface of the water is going to be atmospheric. But that means more energy will be required to raise that fluid when it's open to atmosphere. More energy is going to be required to change the temperature by a single degree than it would have been if you were to keep the volume constant. So we call this heat capacity the constant pressure heat capacity. So is there anything special that we can learn here? Well, yes, there is, but it takes a little bit of math and algebra to get there. So again, this time we know from our heat balance that we have again a closed system. So du equals dq plus dw. We know dw is no longer 0 because work's now been done on the environment. And what do we learn about work from the last lesson is that work is going to be equal to the negative pressure as a function of volume times the differential change in volume. Right? So, plugging all that in, you end up with, which looks nonsensical, but let's go back to our definition of enthalpy. Well, we know that enthalpy is going to be equal to U plus PV, getting it in its differential form. We have differential enthalpy equals differential internal energy plus the differential of the product PV. Well, let's replace du with what we have over here on the right. So we end up with differential enthalpy equals the differential amount of heat added minus the work done, PdV, plus PdV plus VdP, which these two cancel out, leaving us with a very interesting situation. Now, sorry, I forgot to add the Q in there. Now, what did we learn? What was our first condition that we said this was at? Well, we said this was at a specific pressure, a constant pressure. So what is the solution to VdP? Well, that's 0. So in the end, you end up with the enthalpy is going to be equal to the change in the differential amount of heat added. So the change in enthalpy, the differential change in enthalpy, is going to be equal to the differential amount of heat added, which again is going to be equal to the constant pressure heat capacity times the differential temperature. Now, let's go ahead and add another, lay out those partial derivatives again. So let's look here. Again, we have the partial derivative of u with respect to time, or respect to temperature at a constant volume is always going to be equal to the constant volume heat capacity. Similarly, when done against the enthalpy at constant pressure, it's always going to be equal to the constant pressure heat capacity. And to fully flesh out those partial derivatives, what we can say is that the change in u under all conditions is going to be equal to the partial derivative of u with respect to t times the differential t plus with respect to volume at constant t times dv. Right. Similarly, we'll do that for enthalpy. And let's replace these with our heat capacities. And we end up with an equation, a set of equations where we have Cv dt plus, some complex partial derivative here, which we'll elaborate on in a later lesson. But suffice it to say that in an ideal gas situation, which we've not covered, these partials on the right go to 0. This is not the case for non-ideal gases, though they could be small. But what we're trying to show here is that in ideal situations, or in approximate situations, you could say that the differential change in internal energy is approximately going to be equal to the constant volume heat capacity times the differential temperature, and the differential change in enthalpy is going to be equal to, or approximately equal to, the constant pressure heat capacity times the differential temperature. Now, why is this interesting? Well, the reason is because, again, when we're looking at state variables, we're trying to be able to, we're trying to analyze and do heat balances across the system. If we know the temperature on the in and out of a system, or the beginning and end of a system, depending on if we're looking at open and closed systems, if we have all of our degrees of freedom satisfied, and all we know, and we are able to calculate, at least in some way, shape, or form, whether we're told or measured, we have T1 and T2, and the system's a pure system, then as long as we know, how CV or CP changes with respect to temperature, we can take these integrals and calculate the actual change in internal energy and the actual change in enthalpy. And this will tell us, depending on the situation, how much energy had to be added to the system. Right. Again, in an open system, right, where we're under, steady state situation where we have a, the change in internal energy with respect to time is 0, then we're looking for how does the enthalpy change, and all we need to know is the temperature at point 1 and point 2. Similarly, in a closed system, all we need to know is the temperature at time 1 and the temperature at state 1 and the temperature at state 2, and we'll be able to calculate the change in internal energy. And from those calculations, we're usually able to calculate the amount of Q added to the system. Right. So, in a closed system, however, let's just talk about a closed system for a second. Which one of these values is going to represent Q? Well, again, it all depends on whether it's a constant pressure process or a constant volume process. If it's a constant pressure process, guess what? It's going to be DH, right? So Q equals DH if it is a constant pressure process, whereas Q will equal du if it is a constant volume process. And Q equals neither otherwise. I want to say it like that because if it's isothermal or adiabatic, Q won't follow those two. But the interesting thing is you don't need to know Q to be able to determine the change in internal energy or change in enthalpy. You just need to know temperature. And that should highlight to you a little bit the difference between what we call a state variable and a path-dependent variable. There's lots of different ways to get the internal energy to change from one state to another, right? there's lots of different ways to change the temperature, let's say, from one temperature to another. And that's not necessarily just adding temperature, or adding heat, excuse me, but it could be a variety of other things. But in the situation where we have a constant pressure, again, you can determine that the Q is exactly equal to the change in enthalpy. And in the case of a constant volume, the Q is exactly equal to the change in internal energy. So that was a lot to really discuss in a very short amount of time. But now we have everything we need to know to be able to do some real practical examples, looking at both closed systems and open systems, and our heat balance. So I hope after we do this next recap lesson, we'll be able to get into some real examples. But I hope you enjoyed that video. If you did, please like, comment, and subscribe. Thank you, guys.